This is the lists here that I mentioned. Joe Orman had devised the Naked Eye 100, and then that's just a screenshot then of the website Aeramo, that an observer has taken Joe Orman's list, and they've taken photographs of each of the phenomena as they observe them, keep a record of when they actually saw it, and even have a record of when they might next see a particular event, such as a solar eclipse, for example. Now, Joe's list, some people kind of felt it was too easy, but I think it's a wonderful list to start off with. If you're just getting into the hobby, and you'll find that it'll encourage you to go out and observe quite a lot of these sites, and to be aware of the sites as well. One item in particular that, well, two items you can actually cross off the list. Number one is the solar transit of Venus, because the next one won't be for about 100 years. So the last was in 2012, and there's roughly 130-year gap between each pair of transits. And then a solar transit of Mercury, although we'll see more of them over the next couple of decades, Mercury is just too small to see with the unaided eye, silhouetted against the solar disk. So that entry in Joel's list should really be supplemented by something else, and the transit of Venus. But that, again, that's the beauty of these lists, that you can play around with them and add in different things, like sightings of the space station, for example. But to kind of, in learning to see, we probably should learn a little bit more about the human eye. And in a way, you could compare the eye to a digital camera, because as with a digital camera, there's a lens, we like focus the image, we record the image, and we change the aperture, for example, to allow in more or less light. And there's lots of other aspects as we go through the next few slides, where we'll compare the various features of a camera with the human eye. And to start off with, the sensitivity of the human eye is very much involved in learning to see in astronomy. The human eye is basically lined with cones and rods, various receptors that pick up light and feed it through the optic nerve to the brain, where an image is formed, the same way as light comes in through the aperture of a lens and falls on the sensor in a digital camera, or a film in a film camera. The human eye is lined with roughly maybe 100 million rods and about 9 million cones. The cones are the color sensitive kind of receptors in the human eye. There's actually 3 types of cones that pick up different colors: red, green, and blue. And those are sensitive to different those particular wavelengths of light. When light split up into constituent colors, each wavelength of light corresponds to a particular color. And in terms of the cones, the colors they are most sensitive to, the combination of the signals hitting the cones allow the brain to mix those colors and see the world in color around us. The cones are also concentrated in a particular area of the eye. They're concentrated around the macula, which is offset from the optic nerve. The optic nerve corresponds to the blind spot of the human eye. It's where the nerve goes from the back of the eye into the brain. Overall, that concentration of the cones around what they call the macula, and then an even more intense concentration, about 0.3 of a millimeter across, occurs at the fovea centralis. And that's where the sharpest part of the human eye is. The rods, though, are spread much more around the back of the eye itself, though they too are concentrated slightly offset from the optic nerve. And that comes into play in terms of using a technique what astronomers call averted vision, where instead of staring directly at a faint galaxy through a telescope, for example, you look slightly off to one side, but concentrate on the object you're looking at through the eyepiece, and the light falls on the area of the eye where the rods are more concentrated, and you can see that fainter light a bit better. And it's quite a surprising technique when you use it for the first few times that it really works. But that concentration, like even though there's between the numbers of rods and cones, there's roughly 120 million of those photoreceptors, but there isn't as many what they call ganglions then connecting to nerves in the or kind of nerve cells in the optic nerve. What that means is only about 10% of the light that we're receiving is being passed along to the brain. All the photoreceptors are not all sending information at the same time directly into the human brain. The brain can only process a certain amount of information. So only about 10% of what we're basically seeing is going through the optic nerve to the brain. When it reaches the brain, the image is upside down, the same as through an astronomical telescope, but our brain automatically flips it right way up for the world we see around us. That sensitivity is also important to astronomy in that the rods contain a chemical called rhodopsin, or the more popular term for it is visual purple. And what that means is that when you go outside in a dark sky, and the more time you spend outside, the more that visual purple builds up in the rods, and the eye becomes more sensitive to dimmer light. But visual purple is destroyed by bright light. So if you're outside and you've been outside for 15 minutes and your eyes have got really dark adapted, and then someone shines a bright light in your eye, then that visual purple is destroyed, and it takes maybe another 15 to 20 minutes for it to build up again. And it's the reason why astronomers get extremely irate if you're out observing and someone starts shining a bright light, or if a car pulls into a car park and with the high beams on and floods the car park with bright light. It'll literally just destroy the dark adaptation you've had. And that's why astronomers use a red light, because the red light helps preserve that dark adaptation. Now, the thing about that is red mightn't necessarily work for everyone, because there was a Sky and Telescope article a couple of years ago where they were examining, I guess, what they would call the myth of the red light, because they found that actually the kind of light, the kind of warm yellow from a candle flame is probably even better than a red light. So it does actually vary between observers. So it's almost worth trying to find out if a red light is better at preserving your dark adaptation, or whether maybe a slightly different filter on the front of your torch might be better. So it's worth kind of playing around with that. In terms of the aperture, like the aperture in the camera, your pupil opens and like widens and contracts depending on the amount of light. During the day, the pupil in the human eye contracts, but at night it opens quite wide. Now, the amount it opens by varies with age, as the table shows. Like a young person, their pupil dilates to about 8 millimeters at night. But as you get older, it shrinks a little. And that's quite important. So if you're picking a pair of binoculars, or even a telescope eyepiece, because if you've got, like, say, a pair of 10 by 50 binoculars, you divide the 10 into the 50 millimeter is the objective diameter, the 10 is the magnification of the binocular. You divide 10 into 50, it gives a 5 millimeter exit pupil. If you've 7 by 50 binoculars, 7 into 50 goes roughly 7 times, so it's giving a 7 millimeter exit pupil. Now, if you've like small pair of binoculars, like the pocket-sized ones that have an aperture of 21 millimeters and a power of 8 times magnification, you divide the 8 into the 21, you get less than 3 millimeters exit pupil. What that means is that if you look through those pocket binoculars, the cone of light coming out of the objective eyepiece, or out of the eyepiece of the binocular, is only 3 millimeters wide. But if your pupil dilates to 6 millimeters at night, then that cone of light is not taking full advantage of, like, is narrower than the width your pupil is dilated to. So the image actually looks dimmer to what you're seeing just by looking up. The same with if your pupil dilates to only 5.5 millimeters, but your binocular has a 7 millimeter exit pupil, then all of the light coming out of the binocular is not falling on your eye. Some of it is not reaching going through the pupil at all to the photoreceptors at the back of your eye. So it's worth optimizing your binocular to roughly your pupil diameter. You can use an Allen key to kind of estimate your pupil diameter. There's various techniques to try and guesstimate, or you can get what's called a pupil gauge. I don't have my one here with me at the moment, but a pupil gauge is quite easy to use to try and estimate your actual pupil diameter, and then to try and match your binocular, because then you're maximizing the amount of light the binocular is delivering to your eye. The reason sharpness, like aperture, is also related to the sharpness of your eye. During the day, we see point sources quite sharp, but yet we don't see that same sharpness at night when our pupils dilate. And that's because the dilation is controlled by muscles around the pupil, and they pull unevenly, or there's slight irregularities, kind of microscopic irregularities around the pupil, and the slightly different tugging in different directions creates aberrations in the eye, creates distortions in the eye. So the more the pupil dilates, the less sharp it becomes. One way that's quite apparent is if you see fine spider silk just kind of backlit by the sun, you can see extremely fine spider silk maybe just hanging from a branch or spread across some flowers, and yet your eye during the day can easily see that spider silk. But it would be impossible to see it at night if it was visible, because that sharpness to pick up so fine an object at night is near impossible for the human eye to do. If we could see with that same sharpness at night, all of us would easily see the phase of Venus. When it's a crescent, the reason we can't see, or very few of us can't see the phase of Venus as a crescent, or even the satellites of Jupiter separate from the disk, from the planet with the naked eye. There is some people have managed to do that, but it's very, very rare you hear of people having the ability to see one or two of the moons of Jupiter distinctly separate from the planet. It's because our eye just isn't delivering that sharpness at night. There is a way of getting around that, though. You could, like if you got a piece of card, for example, and just stuck a pinhole into it, and you held it up to Venus and just hold out the card and try and look through the pinhole, it should be possible to, because the pinhole is delivering that sharpness you're trying to observe. It's cutting out the distortions or the spikes of light or the overwhelming light from the brighter planets, and it should be possible to see the crescent phase of Venus that way. One observer who describes and talks about that technique is Marcel Minnaert, a Dutch astronomer in the early 20th century. His great book is Light and Color in the Outdoors, and Minnaert focuses a lot on atmospheric phenomena, but he also explores a lot about ways of learning to see and techniques of for the naked eye observer to push the boundaries, essentially. I guess one of the ways of improving the sharpness is these are night myopia flippers that opticians would have, and essentially they allow you to test your visual acuity. If you that article mentioned there are spectacles for spectacular skies. It basically is where describes how people have optimized pairs of glasses. Like these are my astronomical glasses. The diopter is actually about 0.75 greater than my normal prescription. And basically I used the diagnostic flippers on the full moon, and they cut down the glare and increased the sharpness of the visibility of the lunar disk. Also allowed me to see much closer double stars with the naked eye than I could just by using my ordinary glasses. When like Specsavers were doing the 2-for-1 offer, so when I got my normal glasses, I said, can you give me the second pair, but with the prescription improved on them? And when they asked me why, they had to have a think about whether, because they said no one has ever asked us for this before, but certainly it's worthwhile doing, because you'd be amazed at how sharp a view you get of the sky with a second pair of glasses, the prescription bumped up. This slide also talks a bit more about sharpness, in that the human eye, it's rather like a film camera or a movie camera rather than a static camera. It's not taking like a snapshot and then feeding it back. It's continually scanning the scene. Involuntary movements of your eye that you're not even aware of are basically filling in the sharpness of the image around you. But if you stare at a particular, say, piece of text on the screen or a page on the newspaper and just stare at it, you'll kind of become aware that it's only the center of the image is actually sharp, and the rest of the image is blurred. And that's because I mentioned about the macula, the fovea centralis, the sharpest area of the eye. The human eye at that point is like, it's using the cones, which are heavily concentrated in that region, to create the sharpest image possible. But the involuntary movements then are filling in the scene, so your eye is continually filming the scene around you and creating that sharpness. In fact, the center of the eye, the sharpness there is equivalent to about a 74 megapixel camera, but the sharpness of the human eye overall, if you took the full eye, is about equivalent to a 574 megapixel camera. So, but it's that central fovea centralis part that if you're staring at something, that's where the sharp image is falling on, and the rest of the scene around is blurred. You'll actually, if you try it, you'll become aware that the rest of the slide, for example, is blurred, and just the area you're staring at without moving your head or your eyes is completely sharp. Well, it doesn't look sharp on the screen there, except right in where it says DOF in the center of the image. But it kind of approximates what the eye is genuinely seeing. That sharpness also equates to, as it's saying there, the human eye being able to perceive a lunar crater down to about 85 kilometers diameter, or about 30,000 kilometers diameter approximately. In other words, maybe 2.5 times the diameter of the Earth is the smallest sunspot you can see. So it's still quite a big sunspot. Color perception, I spoke a bit about that. During the day, we're using both cones and rods, but at night, rods are not color sensitive, so we see the scene mostly in grays. We've lost a lot of the color perception, but also, as I mentioned earlier, our visual acuity decreases because of our pupil dilating and the inherent aberrations that occur. And then lastly, as well as your eye, sky conditions play an important part, because no matter like how good your eyes are, if your local sky conditions are not good, then you won't get great views of the sky. In fact, a few years ago, when I was down in Ballinskelligs, the sky was so dark, and I got so dark adapted that I actually was seeing the sky as grey, not as the black of night. And what I was actually seeing was air glow. The molecules of the upper atmosphere excited to glow during the day by sunlight and releasing that energy at night. So it showed how dark the sky really was. Like transparency, like observers often look for like there's often good weather or good observing after heavy rain has passed through and washed a lot of the pollutants out of the atmosphere. If the stars are twinkling like crazy, it's not a great night for observing some celestial objects because they're going to be affected by where the image, you just can't get them focused in the eyepiece because there's so much air currents that the image boils in the eyepiece. But on to the lists or the phenomena that you can see. I mentioned earlier about the various lists done by Joe Orman, and these lists were drawn up to encourage people to be aware of a wide range of sky phenomena you could see with the unaided eye. The lists are a mix of phenomena that you can see, but also whimsical. Joe Orman's last item on his list is fall asleep under the stars. And a nice thought because like just lying there, taking in the universe on a summer's night with the Milky Way arching overhead, it's just, you feel a real connection with the universe. And some of these lists might take a lifetime to finish. The second of the books that Bob King wrote was Wonders of the Sky, the Night Sky to See Before You Die. Now, not all of the objects listed in this particular book are things to see with the naked eye, but some of the phenomena are extremely rare. Like there's been no supernova visible to the naked eye in our galaxy since the invention of the telescope. We're long overdue one. Betelgeuse had a dimming or a fainting, to use the proper term, a couple of winters ago, and people were wondering, was it a precursor to a glowing supernova? It would be an extraordinary sight. Another of Fred Schaff's books is called The Starry Room, and he has a chapter called The Next Supernova and describes what people would see. It would, if Betelgeuse went supernova, it would be as bright as the first quarter moon, but concentrated to a point source. You'd actually see your shadow cast on Earth from the light of Betelgeuse as a supernova. It would also be, because it's a point source, it would also twinkle like crazy as it grows, and that would just be an extraordinary. And it would also unite everyone worldwide to look skyward in wonder and maybe just put aside all their differences. The various lists that you find allow you just create your own variations. I say there, think outside the box. Like some observers have come up with different ways to see these various phenomena with the unaided eye. And as the author of the Astronomy website does, they record what they see with photographs. People can do it in lots of different ways. And as you look back over the list, it will remind you not just of the things you see, but it will show your progression and development as an amateur astronomer. And lastly, have fun doing this because these are phenomena you can share with others, and explore the sky with others is just a fantastic way of appreciating. In fact, I often think, like, it's so true. They say, look at the world with the eyes of the child in wonder, and the same with the sky. Look at the sky with the eyes of the child in wonder. I'm still as excited in seeing a rainbow as I was as a kid, because there's so many aspects to rainbows that as you become aware of them, it really enhances your wonder of them and the simplicity of how they occur. The first object we look at is the moon, and this was the supermoon last year in May of last year, coming up over Killiney. That jogger there was running up and down the beach, and all the pictures I was taking, they were blurred. And then they noticed the moonrise, and they just stopped and looked, as I said, in wonder. And I managed to get that photograph when they froze for just a moment. But the ever-changing aspect of the moon for many people, it was just a mystery, and the phases of the moon can be mysterious, but they're also quite exciting to follow. When the moon is first quarter, you can take you can take a ping pong ball, and if you hold it out just in front of you, and the sun is off to your right as it sets, and it's first quarter moon, the first quarter moon will be due directly south. And if you hold a ping pong ball out in front of you, lined up with the crescent or the first quarter moon, you'll notice that one side of the ping pong ball is illuminated by the sun about to set. And it's a great visual demo of understanding the phases of the moon, the ping pong ball representing the moon in orbit around the Earth. This is what's called a moon phase wheel. There's plans for them on the internet, but they allow you to dial in whatever the phase is, and it will tell you when that phase rises and when it sets. So people are surprised that the moon is visible during the day. And this is the moon phase wheel is one way of being able to learn about these ever-changing aspects of the sky. The orientation of the moon's phase changes over the course of the year. The same phase, the crescent in the spring is quite high in the western sky, and the horns are pointing upwards, it's the bow towards the horizon. But in the autumn, the lunar crescent is standing more upright. So watching that ever-changing orientation of the lunar phase is quite interesting as well. Even the markings on the lunar disk, they appear tipped over towards the left. The dark seas of the lunar disk appear kind of, the moon kind of appears tipped over on its side. And then as the full moon is due south, it's more upright. And then as it's setting towards the west in the morning, the lunar seas are tilted more towards the horizon. So that whole changing orientation of the moon, the phases, it's an extraordinary phenomenon to follow, because you'll find that the aspect of the moon changes all the time, and just seeing a lunar crescent when you come around the corner, you could have had a busy day and just feeling a little down. And so many times I've just come around the corner of driving along, and suddenly the road is going west, and there hanging to the west is a remarkably thin lunar crescent, and it just gives a wonderful lift to the day. It's almost like the universe has a surprise lined up for you, and just reveals it and says all is good with the world. The other interesting aspect of the lunar disk, like the introduction to this section showed the supermoon. It's a term that's crept into common parlance over the last few years. one thing that does set my teeth grinding, though, is some websites use the term micromoon for the smallest full moon in the year. I just think that's I just can't accept that term. Supermoon, fine. Micromoon, no, definitely not. Be gone. But the moon's orbit, the reason we see the moon's size vary over the course of the year is because the moon's orbit isn't perfectly circular about the Earth. It varies from like 356,000 kilometers to around 405, 406,000 kilometers during the year. Anthony Ioannidis in Athens in Greece, he took these series of photographs using the same camera setup, and it recorded a genuine apparent size change because of the close moon and the most distant moon. The most distant moon of this year was last January, and the closest full moon is July. And you can see how hard it can be to actually judge the apparent size. When you see a regular full moon slotted between the most distant full moon of the year and the closest of the year, it is actually quite hard to pick out the apparent size. There is a few ways you can track the change in apparent size over the course of the year. You can use what's called like you can create a cross staff which can measure the apparent diameter and plot it on a graph, and you will see a genuine change. Or even some observers have even just stuck a piece of white tape to their thumb, held out their thumb, marked the apparent size on the piece of white tape, then used the same piece of tape each month for 12 months. And just by holding their thumb out, your thumb will actually cover the full moon. In fact, you could cover the full moon with your little finger as well. But just that technique allows them to just with a marker, piece of white tape, holding out your thumb, you can measure the apparent change over the course of the year. Of course, the other change is due to the so-called moon illusion, which is a psychological effect. In fact, if you look at this optical illusion here, the two orange circles are the same physical diameter, but the one on the left looks smaller than the one on the right. But it's purely down to an optical illusion. The same phenomenon of the moon illusion is worth discovering in other aspects of the sky. For example, in December, late November, when Cygnus the Swan is sinking towards the west, it's remarkable. The constellation actually looks bigger with respect to the horizon than when it's directly overhead in the summer months. And it's worth trying. Like if you look at Cygnus when it's overhead during the summer, just fix in your mind how big it looks to you when it is at the zenith. And then towards the end of the year, have a look at Cygnus again on a clear night when it's setting, and you'd be surprised. It actually appears to cover a bigger area of sky than it did when it was overhead. I've even seen the same effect with a couple of the planets like Jupiter and Saturn when they were a little bit away from each other, when they were in the south part of the sky at their highest point. They just appeared normal distance from each other, but then when they neared the horizon, they almost appeared as if they were further apart than they really were. And it's a remarkable effect, and one you can discover for yourself. Other lunar phenomena that you can see with the unaided eye are the changing colors of the moon as it rises, the light being absorbed, and the shorter wavelengths being scattered more than the longer wavelengths can cause the same way as we see a reddened sunset. The moon appears red as it's rising, then it changes to a bronze color, then a golden yellow hue, and then eventually a chalk white when it's in a darker sky. And there was a wonderful astronomical picture of the day image a couple of days ago, which showed the different colors of the full moon over the course of the year. And it was just remarkable how many colors it can take on. Earthshine is so simple a phenomenon, but yet has fundamental importance even in modern astronomy. It was first correctly explained by Leonardo da Vinci, who explained that it was due to sunlight bouncing off the day side of Earth onto the unlit portion of the moon and back to the observer, who saw the unlit portion of the moon faintly glowing against the brighter crescent. It's worth kind of seeing how late a phase you can see Earthshine. I've seen it just up to almost first quarter moon, so it's worth kind of exploring. And the intensity of Earthshine varies based on the cloudiness on the day side of Earth. When it's after sunset in Ireland, it's still daytime out over the Atlantic. So sunlight bouncing off clouds out of the Atlantic, off the unlit portion of the lunar crescent back to us. If there's heavy cloud out in the Atlantic, Earthshine can appear just that little bit brighter. I mentioned its importance in modern astronomy. When they directly observe extrasolar planets with their parent star, those planets are shining by virtue of reflected sunlight, and astronomers take a spectrum of the star, a spectrum of the planet, subtract one spectrum from the other, and they're left with just the constituent kind of, I guess, elements that are in the planet's atmosphere, and they can infer whether there's biomass or it can support life. And Earthshine allowed them practice that technique by taking a spectrum of Earthshine off the Earth's moon. They were able to see biomass signature of life on Earth. So that same technique is being applied to in observing extrasolar planets. Other naked eye sites, Mare Crisium, the circular sea in the top right of the lunar disk. It sometimes appears difficult to see, just a very thin line near the lunar limb, but other times it's quite easy notice. It appears quite far in from the lunar limb, and that's due to a phenomenon called libration, an apparent rocking of the moon on its as it goes around the Earth, that sometimes allows us peer a little beyond the edge of the moon or over the polar regions of the moon and see features beyond. And it basically allows us to observe 59% of the lunar disk from Earth, though of course we only ever see 50% of the disk at any one time. But with the naked eye, you can actually discover libration for yourself by observing the changing aspect of Mare Crisium. The Pickering test is more sophisticated. It is trying to see the smallest lunar feature with the naked eye. The best time to actually attempt that is when it's the full moon in the morning sky, because if you try and observe the full moon with the naked eye during the night when it's high up, there's too much glare, it's set against a darker sky. But in the morning time, the full moon is set against a gradually lightening sky, and, and the disk, the glare is much more subdued. In fact, the glare is virtually non-existent as the sky begins to lighten. And you can see significant amount of detail on the lunar disk with the unaided eye in the morning times. And it's worth trying, because there's some mornings I've done that and I've just been amazed how much detail I could see with the naked eye on the moon. The sun, there's various things you could do with the naked eye, for the naked eye observer with the sun. I mentioned earlier about its changing aspect along the horizon. If you plot the sun's position over the course of the year, you'll find that it oscillates, say in the evening time, between west-southwest and west-northwest. It'll progressively move right until at the June solstice it reaches its most extreme point. And then after the June solstice, between then and September, it'll move left. And then after the September equinox, continue progressively more left until it's due west-southwest on the December. And that's worth kind of just keeping a note of, because you can like just make these discoveries for yourself. Like if you photograph, say once a week, the sunrise, or sorry, the sunset point over the course of the year and create a time lapse, it's really remarkable the way it oscillates back and forward along the horizon. When the sun is setting in the west, if you look east, generally in the winter months and the early spring, it's more pronounced. You can see a phenomenon called the belt of Venus, this pinkish glow along the eastern horizon, where sunlight is still bathing the upper atmosphere, even though for all this down on the ground, the sun is just after setting. And then below that pinkish glow, you'll see a grey band, which is the Earth's shadow projected onto our upper atmosphere. And that gradually rises, the pinkish glow begins to dissipate as night begins to fall. And then the cloak of night gradually meets the Earth's shadow, and night fully descends at that point. But again, it's a phenomenon that people may have seen, but not have been aware of the cause. Naked eye sunspots, and the sun is building up again to solar maximum, which is expected in the year 2025. And already in the last kind of year and a half, there has been some naked eye sunspots, but none on the scale of these ones here, which were visible in October, late October 2003. The biggest spot group there is about 40 times the surface area of the Earth. And all three were easily visible to the unaided eye that was safely protected with a pair of eclipse shades. Like these have filter material that reject 99.9% of the solar light and allow you to safely look at the sun. I forgot to bring them with me, but the Lunt do what they call sunoculars. They are 6x30 solar binoculars. They're fitted with solar filters and allow you to observe the sun safely. But with these gigantic sunspot groups, there's always a great chance of the northern lights. And this was a display from Wicklow in 2001, this one picture here. But we will see aurora displays from Ireland, and there has been sightings already early this year from some observers of the aurora, and we certainly expect the consensus is that this solar maximum might be a bit stronger than the last one, which was relatively weak. So there could be a good chance of more aurora in the offing, and certainly websites like Aurora Watch UK, they have a magnetometer hooked up to the internet that gives the current state of the Earth's magnetic field, and if it starts reverberating from the impact of or the accelerated solar wind speeds, then it will alert people if there's potential for the northern lights. The eclipses were clouded out for one earlier this week, but we have some more coming up in this decade, though we have to wait till 2025 for the next total lunar eclipse visible from here. The naked eye observer, although eclipses might appear to be few and far between, they can vary in intensity. The eclipse of December 1992 was extremely dark. There's a scale of what's called the Danjon scale after the French astronomer that devised it. Most lunar eclipses are between 2 and 3 in intensity, but the one in December 1992 was 0.5, some observers gave it, and I'd certainly concur because that particular eclipse, the moon almost disappeared to the naked eye. You had a very hard job finding it in the sky if you looked away. And that was because Mount Pinatubo had erupted in the Philippines in July 1991 and flung a huge amount of volcanic dust into the upper atmosphere, choked our atmosphere with those aerosols, which absorbed the sun's rays and prevented them from filtering through to fall on the lunar disk. So it literally almost blocked any sunlight coming through and created this really dark eclipse. Like I could see no color with the naked eye at all. In fact, the description I used at the time was it looked like a very tarnished ball bearing in the sky, and it really looked three-dimensional. It was very striking. Solar eclipses, we have to wait till 2090 for one from Ireland. Well, a total, but this decade is remarkable in that, except for 2023, we have a partial solar eclipse every year. Now, the thing is that some of these are partial, but because their totality is accessible or reasonably accessible, then don't stick around for the partial. Make sure you're in the shadow of the moon and the center line of totality. For example, the one in 2024 is total in the United States and Mexico. So definitely it's going to be the next best accessible solar eclipse for us. Or 2 years later, another total tracks over the Iberian Peninsula. And then a year after that, it goes parallel across the northern part of Africa through Libya, Egypt. So there's 3 pretty good accessible total solar eclipses coming up in the next few years for us. The nearer sky, I guess, encompasses a lot of the phenomena we see in the atmosphere, but the area of what you might call atmospheric optics is one of them. That things like rainbows and halos, they kind of fall between astronomy and meteorology, and can be embraced as much by amateur astronomers as cloud watchers. This is an example of noctilucent cloud that was visible back in 2020, and there's Comet Neowise of that year just hanging over the northern skyline out over Dublin Bay. And this was one of the brightest displays in noctilucent cloud I saw for many years. But the blue of the sky, that can vary depending on the amount of aerosols that are in the atmosphere. The intensity of the blue can change during the course of the day as well. This website mentioned here describes a device called a cyanometer. It's basically, it was devised, it was a circular disc with a hole cut out in the center and different shades of blue painted around the rim of the disc. And they allowed people to estimate the intensity of the blue of the sky. An easy way to do it is if you go into your local hardware store and they have the paint chips, the swatches that for different shades of blue, and pick up a few of them in different shades, and you can make your own cyanometer to try and estimate the blueness of the sky over the course of the year or even the day. You could also pick up even ones that are in different shades of reds and oranges, and that would allow you to estimate the color of the planet Mars around the time of opposition, because the color of the planet Mars can actually vary as well. If its atmosphere is choked during a global dust storm, the orange is incredibly intense, whereas when its atmosphere is much more clear, the orange tint to Mars is just that little bit more subdued. And again, it's a phenomenon over the years you'll begin to become aware of if you're observing the sky with the naked eye. Rainbows, I mentioned, I'm still as fascinated by them as when I was a kid, and certainly the like halos can come in all forms and intensities. Like rainbows, for example, when you see them, you'll notice that the sky is brighter inside the bowl than outside, and that's due to preferential scattering of light in one particular direction. And in the secondary bowl, light is scattered to outside the bowl, so it creates this dark stripe of sky between the two bowls that's nicknamed Alexander's dark band after the philosopher that first described it 2,000 years ago. I mentioned noctilucent cloud. These are clouds that form up in the mesosphere, about 80 kilometers high, and they are where ice crystals condense around what they think is meteorite dust, and they become visible during the summer months towards the end of May into mid-July. And the displays can be quite striking. They look like cirrus cloud, and very often you might see lower down clouds silhouetted against them, while because of their great height, they remain illuminated by the sun below the horizon, even though the world below is in darkness. Dust of other kind permeates the inner solar system, and there's various debates as to the source of that dust, from comets to recently I was reading that Martian dust storms might even be responsible for some of the replenishing some of the dust, because the particles whipped up into the upper atmosphere of Mars may reach escape velocity and escape the planet's gravity and then permeate the inner solar system. But the zodiacal light, it's a faint cone of light you see tapering up from the western horizon in spring evenings from a very dark side. And then there's a proliferation of satellites and the likes of heavens above. detail space station passes, but also kind of various other satellite launches, including the ubiquitous Starlink trails. I think it was last year that we found there was going to be a deorbit burn by the upper stage that launched the Landsat 9 satellite, and we managed to catch the outgassing from the rocket as it was decelerating to re-enter the Earth's atmosphere. And that was one of the most remarkable sights I've ever seen. In fact, a recent Starlink launch a few days ago, there was a similar deorbit burn by the upper stage that observers across the UK managed to photograph. Then, like I'll kind of speed up a little here, but the observing the planets in the solar system with the naked eye can be quite intriguing. This is Saturn, or Jupiter and Saturn, just a few months shy of their very close gathering on December 21st, 2020. And there were still spaced a bit apart at that stage, but the gap rapidly closed because Jupiter moves roughly a moon diameter every 6 days. So it quickly caught up with Saturn. And the gap has now widened significantly again until the next so-called Great Conjunction in the year 2040. But many of these conjunctions and groupings can be found listed in the 2 annuals that come out roughly around September every year. The late Heather Cooper used to co-author with Nigel Henbest the Phillips Stargazing book, and then Sturm Dunlop, along with graphics by Will Tyrion, the famous Dutch uranographer. They produce the Night Sky Guide published by Collins, and those 2 are definitely worth picking up every year. They'll list all the fine groupings of the planets in the sky that are worth going out to see. In fact, the end of this month, the end of June, all the naked eye planets will be visible in the morning sky in the order of their distance from the sun. So you'll have Mercury, Venus, Mars, Jupiter, and Saturn spread across the morning sky. June 24th, the moon will be between Venus and Mercury, but June 27th might be the best date because then Mercury is directly below the moon, so it would be easiest to find the innermost world by using the moon as a guide to find it. Meteor showers during the course of the year. Many observers gear up for the 2 big showers, or the Geminids and the Perseids in August. And then every so often a remarkable comet appears and really gets everyone excited, and a so-called great comet visible to the unaided eye is just a remarkable sight. The estimate that there's roughly about 78 naked eye comets per century. So over the next few decades, and that's 78 per century over the last 400 years. So if the statistics stay as they are, then we should be in for some nice comets over the next few years. And in fact, some of them do reach naked eye visibility and put on a remarkable show. Getting into the deeper sky, you have the Milky Way, which its aspect just is extraordinary from a dark sight. The billowing bright star clouds with the dark cold gas clouds silhouetted against them. The winter Milky Way isn't as bright because we're looking out of away from the center of our galaxy towards what Mick McCreary has written about before, the anti-center, which is just near that star El-Nath in the Horn of Taurus. It's rather like if you were in Galway City, when you look at the center of the galaxy, you're looking in towards the city center. But if you're in the summertime, but in the winter time, it's like standing out in the suburbs, looking out into the darker countryside beyond. So the bright lights aren't there. The bright lights we do see in the winter sky are relatively nearby stars. The because the eye is poor at seeing color at night, it's really only the very bright stars we'll actually see any color in. But there's certain projects you can do in the winter sky, for example. It is possible to see some subtle color differences in the stars, and it's worth kind of training your eye to perceive these color differences. Some stars that vary in brightness, you can follow their variations with the naked eye, like the star Algol. Other stars, the estimate may be 60% of the stars in the sky are not solitary. They've a companion or one or more companions. And one of the most famous examples is Alcor and Mizar, the middle star in the handle of the plough. If you look closely, you can see bright Mizar has a fainter companion, which is Alcor. And with these, using the optimized glasses or those flippers, diagnostic flippers, you can make out some even closer double stars. You can just see a gap between them. Again, it's enhanced viewing, but again, it's a nice naked eye observation. Looking more distant, there's numerous naked eye clusters and other so-called deep sky objects you can see with the naked eye. I was down at the Dark Sky Reserve in Kerry at the beginning of March, and I was really amazed at the number of naked eye clusters I could see in the winter sky. It was just an extraordinary sight to be under such a dark sky, and these clusters really, now there were just blurs of light, but by comparing where I charted their position against a star atlas afterwards, I was able to tick off quite a few naked eye clusters that I had never seen with the unaided eye before. And just to wrap up, I mentioned some of these authors, like Fred Schaff, Bob King, and Marcel Mineret, but there's others out there that write and cover aspects of the naked eye sky, and they're worth seeking out these books or the articles that they've written. You could basically spend your whole life in amateur astronomy, purely exploring the sky by eye. And if you want to know more, drop me a line. I'll convert the show into a PDF and I'll send it on to Sinead so it can be shared with everyone. But feel free to drop me a line, as I said, or to throw out any questions you might have. And thanks very much for the invite.